No, no, no. Mm. Mm. Right. Okay. And then let's do that.
So you cannot share that screen with your wife or somebody. But.
Okay, so master, can you see the screen now? My screen.
Yes, sir.
Okay. What's that? I actually don't. So I've given mine to Brogan. Right. So the master, can you see the notes there? It says population modeling.
Yes, sir.
Okay, like it. All right. Okay, guys. The master, you are the announcer. When somebody else arrives on the meeting, hopefully a few more people arrive, you announce to me, please. Okay, so I know who's
Okay,
online. Okay, right.
Okay.
All right. So modeling. Okay. Well, actually, sequences and series. Sequences are models. Okay. So and we have two main types of sequences, the way we express it. Okay, right. Explicit, general, and recursive, which are also called difference equations. Okay. Just scribble on the back of it somewhere if you want to. Okay, difference equations. Okay. And you get two types of difference equations. First order difference equation and second order. Okay, difference equations. But there are two ways we can express sequences. So you can remember, you don't remember what an explicit formula is or a general formula.
TN.
The TN is generated based on what? Is that one of ours? The PN.
Yes.
They're not thinking that they cannot do no lesson. Will I have it? Let's see how every student think. Will they think? Will they be actually going to be?
So just it's in your class. Yeah, Roger was just gonna leave you.
Okay, well, I mean, this is where I'm teaching this. Okay, right. Okay.
Yeah,
I
get to do bring cookies. I did bring cookies. Yay.
Okay, right. Okay, let me cut it. Okay.
Yeah. Oh.
Okay, we'll do
Okay,
this.
sorry.
Yeah.
Oh, I'll just put it on the floor.
All right.
Can I?
So now, okay, in a general formula, Tn is generated by, if you know n, okay, so you can put n into a formula, okay, and what comes out is Tn. So they're very easy to work with. The problem is that quite a lot of models cannot generate a term based on n. Not possible. Yeah. Whereas a recursive model or a difference equation, just another name for the same thing, just like explicit and general are different names for the same thing. Okay. How do these work? Okay. Well, if it's a first order difference equation, okay, Tn, you know, Tn minus 1, okay, and you put it in to the formula, okay, what comes out is Tn. So in other words, it depends on the one previous term. Okay. Sometimes we go Tn, this means the same. So Tn minus 1 means the term before term n. So if you know this, you put it into your recursive formula, what pops out is term. It depends on the term before. Okay. Disadvantages are what? Well, to figure out term 50, you have to first know term 49, term 48, term 47. Okay. The advantages are that there are a lot of sequences which cannot be generated, okay, by an explicit formula that can be generated by a recursive. Okay. And just some of you get confused by the fact that I'm saying the same thing as this. If I said that if I put in term n and I apply the recursive formula to a first order difference equation, I'll get term n plus 1. Okay, you've got to be comfortable with that notation. That means the term in position n, that means the term in position n plus 1. Okay. Am I making sense? Okay. A second order difference equation, to get Tn out of it, what would have to, you'd have to know Tn minus, you'd have to know the two terms preceding that. So like a Fibonacci sequence. Okay, so you'd have to know term n minus 1 and term n minus. Okay, so it depends. Okay, on two previous terms. Big sport afternoon. You guys are excited. Wimbledon. I don't remember what I said, but I don't remember my watch, but even more importantly, what? It's an epic stage in Tour de France today. Go to channel 205. Go to channel 205 at 4:30 today. And watch the last 45 minutes of today's stage. That's because of machines. Okay. They are human gods that die as machines. Okay. All right. Right. Anna, do you want to close the door? Okay. Right. For now. Okay. I've got a story.
Where? Too small. That's fine. That's what I hope for sometimes. Oh, wait. No, you're writing tomorrow. That's a big one. When did we start?
Okay. All right. So now, okay. If I'm carrying on left and right. Okay. So we on the left I've got explicit and on the right I've got recursive, right? Okay, so you all know this. So if I gave you an arithmetic sequence and it's a very easy one, it's 2 plus 5 plus 8. Okay. As an explicit formula, what would that be? So you could go with a plus n minus 1b. Remember that? Okay. Or you could say, did by inspection, what's the difference? Here we go. So you say the difference is 3, so the coefficient of n must be that. Then you balance it. If you sub in 1, you get 3. Do you use this or do you use a plus n minus 1d? Yeah, I'll also use this always. Okay. You can use a plus n minus 1d, it'll work, right? Where a is the first term. But I just said the difference is 3, so it's 3n. Hey, I'll put 1 in at the moment. It's like subbing into an f of x equation. T1 is 3 times 1 up to 3, but what should it be? It should be 2, so I've got it. Okay. Plus n on a plus n minus 1d also going to work. Okay, right. So there's the answer you should get no matter which way you go. Okay, right. However, okay, so what would that be as a recursive formula? I could say, well, if I wrote Tn plus 1, what are you doing to get from one term to the next term? You're adding 3, so it'll just be Tn plus. That's it. Okay, and what do you have to write down? You have to write down the value of the first term, right? Okay, so generally in this notation, there we use T1 properly. We're usually going to work in population, we're going to work with P0 as your first value. So T1 is equal to So that both of these things would generate the same theory, right? Advantage of this, over here, this is more useful for this particular type of sequence because I can just go find term 100 by something in anything. Right? So that's what explicit formula does. It generates Tn based on n, whereas this generates a value of a term based on the value of the term before. Yep. I would be shocked if they took a mark for that. Okay. Right. Okay. Now, arithmetic. Right. Then we have geometric. Yeah. Going on the notes here. Okay, so geometric times by constant ratio. So let's have another easy one. 2, 6, 80. Okay. So that one over there, if I said you give a general determine a formula for the general term or find an explicit formula. Okay. Our formula is Tn is equal to AR to the n minus 1. So go write the answer down. So what A equal to? 2 times 3 to the n minus 1. Okay. You cannot times that 2 and that 3 together. Okay. All right. Go write it down as a recursive formula. And I can start with Tn, but if I started with Tn, what would the term before be? Okay, what are you doing to each term? So it's just going to be 3 times term and number 1. Okay, where term 1 is equal to 2. Right. Yes, so if you wrote it like this, Tn plus 1 is equal to 3 times Tn. That's perfectly correct. Same thing. Okay. Right, then you get okay, just want to write. If I gave you mixed kind of question, so this is put under recursive. So I gave you this sequence. Because think of my sequence. I think 2. Okay. Right, click on little mode 1. Okay, right, so I gave you this. Okay. And so you think, well, okay, and I want a recursive formula. Okay, they would really have to say to you, this is the first order difference equation. Of the form n plus 1 is equal to a Tn plus b. Okay, and you're going to find a and b. So you couldn't actually write this as an explicit formula. It is a complicated formula, but we don't really check that. Okay, so then You could use simultaneous equations, but just one is what happens when it's shown. I'm going to give you an old grade 10 test to practice at some point just to remind you of these topics. Okay. What's the difference between 11 and 2? That's not a trick question. 9. Okay. Between 38 and 11? 27. Check in your calculator between 119 and 38.
81.
Okay. So if you do that, now at this, the line of first differences, this line of first differences forms, what kind of sequence is that? 9, 27, 81. It's a geometric sequence, right? And in that geometric sequence, what are you timesing by to get from one term to the next? 9 times what is 27? By 3, right? So your ratio is 3, right? Then A is always going to be equal to that ratio over there. Okay, so in this particular case, we're going to have term n plus 1 is equal to 3 times term n. Okay, so whatever your ratio is in your differences, remember in a quadratic, that those differences form an arithmetic sequence. Quadratic sequence. Okay, but term n plus 1 is equal to 3 times term n. Now, then I just look at the first two terms. My first term was 2, and my second term was 11, right? Okay. If at the moment at the moment, what we've got as our formula? Term n plus 1 is equal to 3 times Tn, right? Okay. If I now go find term 2 would be equal to 3 times term 1, right? You don't have to write any of this down, by the way. Okay. Term 2 is equal to 3 times term 1. So what's term 1 at the moment? Term 1 is 2, right? So at the moment, what's term 2 sitting on? 3 times 2, which is 6. What should it be?
11.
Okay, check. If I put in 11 into this formula, what should come out? If I put in 11, what should come out? 38, does it?
Yeah.
3 times 11 is 33 plus 5 is 38. Someone check for me. If I put in 38, I should get 119. 38 times 3 plus 5.
Yeah, you do.
Okay. All right. So, we're kind of getting my head back into recursive sequences, introduction to this whole thing. So all of the we're going to do 3 population models. Okay, you've done one before, Malthusian, but I'm sure it feels like a million years ago. Okay, so we're going to go and reteach it. So all of your population models that we work with are recursive formulas. Okay, so they generate on them. Okay, so when we talk about modeling, we're always working with recursive, okay, or first order difference equation. All our formulas are those of that format. Okay. All right. Now, okay. Okay. Right. Okay. I'm going to, I hate just reading through notes, guys. I'll read through them quickly now, but I first want to just kind of wing it, okay, with what comes into my head. We're teaching like that. Okay, then I'll come back to the note. Okay. Into them. I also like to test myself that I can teach it really quickly. Okay. Oh, Malthusian model. Okay, so Malthus was a. Okay, you don't have to write anything down. You can if you want to. Some people prefer to write, some people don't. Okay, so the Malthusian. So all of these models are an attempt to try and describe how populations grow. Okay. And they can come into finance as well. They come into all kinds of weird topics. You do anything that involves life sciences or environmental sciences, these models often pop up. There's a fundamental flaw with modeling. Okay, and the fundamental flaw with modeling, it depends on certain parameters, like your growth rate, your carrying capacity, okay, your reproductive rate, whatever it may be. Okay. And models work brilliantly if those parameters are right. Probably if those parameters are wrong. So like carrying capacity, so Kruger Park for the elephants for a long time, they thought there was a certain carrying capacity. It turned out that carrying capacity was completely wrong. Okay, they completely underestimated what the actual carrying capacity was. So sometimes the models work if what you feed into the models is correct. Okay, if you don't feed what if you feed in is incorrect, nonsense N leads to nonsense R. Okay, but theoretically they're wonderful. In reality, okay, they can be of great help, but it's not an exact modeling is not an exact science because it depends on those parameters. So the first guy who came up with an idea of population growth was Malthus, and what he said was that populations, if you plot it in, you don't have to, all of this is in your notes, we're going to go through your notes now. Now we've got graphs of N against Pn. We feed that the population at time N, okay? These are all, okay, what's the opposite of a continuous model from stats? In stats, we had continuous models and we had discrete. These are all discrete models. So strictly speaking, when we draw graphs, they should really be made up of dots, right? So, and our starting point, our initial population modeling, we always describe as P0. Okay, P0 is your starting point in the population. And what Malthus basically said, he said that if you take a population, it grows exponentially. It's a geometric series. There's exponential growth. And we've seen that kind of curve in two places. We've seen that kind of growth described as a geometric sequence. Tn is equal. So this first model actually we can describe in explicit formulas. Tn is equal to AR to the n minus 1. Okay. So in this, if you use this formula for population, there's just something you got to be careful of. I'd never really use this formula when you talk about population. It would work. But the problem is, so you use that notation. But if you're using this notation, you've got to use P1 as your starting point. And we don't normally do that with population growth. So you can think of it as a geometric sequence. It works. Okay. In finance, we've seen this shape. What formula? What this compound interest, right? So you can also think of it in terms of finance, which actually works better than geometric. But in finance notation, we say A is equal to P1 plus I to the N. Okay. But in population notation, we'd say the population at time N is equal to the initial population, which is P0, times 1 plus the intrinsic growth rate, which we're going to call R, to the N. It would work, and it actually works quite nicely. Okay. So this parameter R is the growth rate of your population, intrinsic growth rate. Okay, so an intrinsic growth rate is an optimal growth rate. Okay. All the models, well, the next model as well, apart from Malthusian, depend also works with R. So R is the growth rate under optimal conditions. So if you've got a population and there's plenty of food and there's not much, there's a lot of space for the population to expand. So your intrinsic growth rate is your optimal growth rate. It's all, as I said, it's all in your notes. Okay, but I must have the first to teach this, I think. Okay. So that formula works. It's just different notation. You've worked with it before. Okay. But as a recursive formula, we're going to say, well, let's think about how we get this formula. If you're going from one recursive depends on the term before, right? So Pn plus 1 would be equal to what? Your initial population, or the population before, right? Okay, no, in general, Pn plus 1 will be equal to Pn, plus how much the population increases by, right? And if the population is growing at 20%, it'll be 20% of what you had before. Okay, so plus, if that's your intrinsic growth rate of that population. Okay, so that's your starting population. This is how much it grows, the increase in, I'm going to say years, but it could be any time frame, in one cycle, I'm going to say. In one. Does that make sense? Okay. So that would be your Malthusian model as a, okay, as a recursive formula. And that's what we generally going to use. Okay, now before we get on to this parameter R, which is going to be the most probably important thing here. Okay, what did Malthus actually say happens in his models? What he says happens in his model, okay, is that you get this population. So this is the graph of population. Okay, and then he says, but people need, and we're talking about all populations, yeah, people, okay, animals, whatever, right? But he said food growth is linear. Okay, so he said food growth does this, let's just say, doesn't increase as rapidly as population growth, which is exponential, right? So we've got, but he was wrong, as it turns out. But actually, some populations do work for this. Depends what you're looking at and what's going on. Okay, but he said, and it wasn't a bad expectation, that his prediction was that, okay, here is, Malthus generally looked at humans. And he said, right, food growth is predicted to be linear. And what that means is at some point, population growth is going to outgrow food supply, right? Okay. So what's going to happen is this is your Malthusian, what they call the Malthusian critical point. Okay. And then what happens is the population readjusts. So it collapses, essentially. And it drops right down to a new starting point and starts to cycle again. Okay. So it starts back, drops out here, and then it on with another exponential growth, and that pattern continues. Okay. It does work in the wild sometimes. Okay, you're working in the game reserve sometimes, and there's a dramatic there's really not enough food, the population can drop dramatically. It hasn't turned out to be the case with humans, primarily because the prediction that this growth was linear was incorrect. Okay. We've been able to grow food growth has been exponential, so it's been able to balance generally population growth. Okay. So we've carried on this cycle for a long time. Okay, which is why we developed next model became developed because we realized this wasn't really working. So about years about it wasn't important. Okay, so are we happy with what's going on with Malthusian? Okay, but we're generally going to be working with this formula over here. Okay, so what is this parameter R? Okay, this parameter R is, come on, Roger, is your okay. So there are various ways we think about this thing. What is this R? Okay, what's the name we call this parameter R in population one? Your intrinsic growth rate, right? Okay, your optimal growth rate. Okay. And we can think of R in general, guys. Okay, actually, this may not get it wrong. Okay, if you didn't grade 8 enough, you forget about it now. If I said to you the cost of, I don't know, something, pair of jeans was 1,000 Rand, it's now 1,200 Rand. And if it was 1,000 Rand and now it's 1,200 Rand. Okay, so the initial price was 1,000, now it's gone up to 1,200. How do I work out the percentage increase? Percentage increase is equal to what? The increase over that original times 100. Don't forget that. It comes up in all kinds of weird places. Okay, so in population parameters, R is going to be equal to the increase in population over the original population. It's expressed as a percentage, which often expresses the decimal, times by 100. Okay. Does that make sense? Okay, so that's the fundamental idea of what this value R is. Okay. So, and this thing over here, we call it, it's a rate. Okay. That's going to be your intrinsic growth rate. Okay. So what about this increase in population? Well, in general, what's an increase in population equal to? Okay, number of births minus number of deaths, right? That's the actual increase in population. Okay. So the way we're going to think of R, generally how we're going to calculate R, which is a rate. So your growth rate, the intrinsic growth rate R, is going to be equal to your birth rate minus your death rate. Okay. Where birth rate is equal to number of births in the time frame over the original population. Okay. Not a rate in terms of time, it's the rate in terms of what the original population was. And death rate equals to number of deaths over the population. Okay. The growth rate is birth rate minus death rate. Okay. Can you remember how we found, generally we're going to go find the birth rate? It brings the figures a little bit of a bell. Yes, say it. So, females are more important in population growth. Okay, right. So it's going to be percentage females. So the normal way we're going to calculate birth rates is going to be percentage females. The higher percentage of females in the population, the better the population growth. Okay. So it's percentage of females. Okay. Times by number of surviving offspring. That's what your birth rate is. Number of surviving per population cycle, right? Okay. And the number of surviving offspring is generally going to be something like, I don't know, a leopard has 2 cubs in a population cycle, and that happens twice a year. So it'll be 2 times 2, which is 4. Of those, 60% survive, right? So it's percentage of surviving offspring. So they'll give you the number that are born, and they'll tell you what percentage survive. Okay. So that's going to be your birth rate. Okay. Now let's think about death rate. Okay, death rate is linked to life expectancy. If a lion lives for 20 years, the average lifespan of a lion is 20 years. In 1 year, what proportion of lions would you expect to die? 1/20th, right? Yeah. So when you calculate death rate is going to be equal to 1 over the life expectancy. It's generally going to be percentage survival rate. Survival rate of newborns, okay, times by number of litters per cycle, times by number of kids per litter. That's generally the logic you're going to use to figure out that. This thing over here, the percentage, the number of surviving offspring okay, would be equal to this percentage survival, the survival rate, times by the number of litters per cycle, times by the number of kids per litter. Yeah. Right, so one of the lot. We're always working in one population cycle. All of the things are going to be one. Okay, so I think we need to go straight to, I want to discuss, there's all kinds of other rates that we work with, but I want to go straight to some examples and come back to the notes. Right, so get out your notes. If you're at home, okay, we're going to go straight to, I'm not going to read through this, you can read through this yourself. Okay, we've discussed most of it.
It's missing the off with you.
It's going to be 1 over whatever, let's just have a look at it. Okay. Right, so I want to go to page 4, please. Done these last year or a year and a half ago, but I'm sure it's completely new. Okay. So example 1 on page 4. Okay. Right. Okay. So. Right. At this stage, when I wrote these notes, I think spaniels were the popular dog. Now, what's a popular dog in Parkhurst now? There's just always a dog that's in fashion. What's the dogs that are in fashion now? Right.
Westies.
So in Parkhurst, a rogue population of 400 wild spaniels is increasing at an alarming rate of 12% per year. Determine the number of spaniels in Parkhurst and surrounds after 8 years, using, first of all, Malthusian recursive formula. Okay. I'm going to let you try for a minute.
I've been bouncing. I don't like that.
Okay, so that's our general formula for a recursive formula. Okay, so in this particular case, but just worth remembering for finance and for this section. Okay, 12% is 12 over 100, right? Which is 0.12. Okay, so you end up with p to the n plus 1 is equal to 1.12 times p, right? Pn, sorry. And this is something that's really worth remembering. Okay, if you're timesing by a ratio of 1.12, okay, if you multiply by a ratio of 1.12, okay, what's your percentage increase? 12%. If I had 1.08, what's your population growth rate there? 8%, right? Okay, if I had 2 PN, what's your population growth rate? 100% growth rate, right? Okay, does that make sense? It's worth remembering that. Okay, if I had 1.70, 1.7 PN, what's your growth rate? 70%, really. And that was in finance as well. Okay, so it can just help you. Okay, so that's our formula. Okay, but be careful of this formula, right? This thing, in terms of if R is, it's a bit confusing. Okay, this, if we talk about R as the intrinsic growth rate, R equals R, if I'm referring to R as being the intrinsic growth rate, and I gave you something like this, just so I gave you this thing over here, and R is the intrinsic growth rate, then R would be equal to 0.12, right? It's 1 minus this coefficient. However, if I said to you, describe this as a geometric series, geometric sequence, R in geometric sequence is not the same as R in the intrinsic growth rate. If I was talking about a geometric sequence, R as in the ratio, what are you timesing by to get from one term to the next? R would be equal to 1,1, 2, with it. Okay, so we never really, in this section, we don't really work with this. Okay, we're always going to be working with intrinsic growth rate, but just understand in general, as a geometric sequence, what are you timesing by to get from one term to the next? You timesing by 1,12. But what is your intrinsic growth rate of this population? It is 1 minus that, growing at 12% per annum. Okay. Right. So how did we work out? So your formula is p to the n plus 1 is equal to 1,12 p to the n. If I'm asked to write down a recursive formula, what do I have to write down as well? The starting population P0, which was 400, right? I'm going to remember how we do this in my calculator. Okay, right, let's do this together. In the calculator, what you're going to do. Right, so everyone get your calculators out. Okay, and the first thing we're going to do is what? Put 400 into the calculator, right? Then press equals. Then clear it.
Then answer.
Then you're going to go 1,12 times answer. That'll give you the population of P1. I would always, if I'm using a calculator, okay, a recursive model, okay, to give population, I would also always write down the next population. But sometimes you count incorrectly. Okay, so I would write down the population after 1 year was what? So after you press the button once. What? 448, right? Approximately 448. Okay, but they want to know after 8 years. So you're going to press the button 8 times. So you know, 1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
Okay, and what did you get as your answer? I got 990. You get that?
Yes.
Okay. Okay, so no. So what you should really say, what is it? 990. So you get P8. What did you get on your calculator? 990, comma,
Okay.
comma. 39. Okay, comma 39, right? Okay. So what you should really say is that you have between 990 and 991 statements. I would penalize you. Okay, right. I've never mocked this about it. Okay, strictly speaking, so it's between 990 and 991 statements. I'm too lazy to even answer at that time. Okay. The break at 9:30. Okay. So, peak 11 minutes. So over here, compound interest formula. Instead of using A is equal to P1 plus I to the n, what are we going to say? You can write it down like this. Okay, and you get, I'd say Pn is equal to P0, 1 plus 12% to the n. So it's going to be equal to P0 is 400, 1 plus 12% to the 8. Think you get the same answer?
You do so. You do.
Okay, right. And what do we get as an answer? Same answer, right? Okay. So generally, we're not going to use this.
Yeah.
Okay, geometric we're generally not going to use, but if we did try to use it, you'd have to go t to the n is equal to ar to the n minus 1. Okay, we're not going to generally use it. Okay, and our starting value of a is
400.
okay. Okay, but this is why we don't. I'll show you now why we don't use it. So it's going to be 400. R is still going to be 12%. Okay, now R is going to be not 12%. What's R going to be? Your ratio is 1,12. So that's your ratio. So this R and the R in the population formulas is not the same thing. Yeah. But now the problem is with geometric, our starting point is what? Is T1, right? Okay. The first thing always used was term 1 is your starting point, right? So if we want to get after 8 years, what's n going to be? Okay, it's 9, right? So it's going to be to the 9 minus 1. Because if you 8 years have passed from 1, 1 plus 8 is 9. It's basically down to geometric in this section. Okay? But that's what you'd have to do. No, actually it's 9. Okay, after 8 years, if you start at 1, then after 8 years, it'd be at T9. You with me? That's why I don't use it. But I just want to show you that it's not nonsense. It works. Okay. Because now you're starting at 1. So 8 years of speed release manual fast. Now we're at T9. Okay, so N is 9. Okay. Right, one more time. Okay, page 5. Right. Okay. A young boy collects silkworms with an average life for 52 days. Each female silkworm dies almost immediately. Blah blah blah. After laying about 300 eggs. In breeding conditions, about 35% of eggs reach maturity. Female silkworms account for 70% of the population. The young boy has been given 3 female silkworms to determine the silkworm population after 1 generation. Now, even if they didn't ask you A, okay, they went straight to B. Okay, the problem is all our formulas depend on a sample population with males and females, right? In the sample population. The problem at the moment, okay, I actually made across each a boy collects each female silkworm. I made them add this in because I was like, what? Okay, pregnant. Okay, so, right. Because I mean there were just 3 females and they weren't pregnant. Well, the population's a bit right. Males just some use many of them. Okay, right. Okay. So in one population type, so I could not use this. If you ever get a question like this, where your starting population, okay, does not have males and females, but give me a second. Okay, then you have to move to the next time frame as your starting point. Okay. So we're starting off with 3 females, right? Try to do A. You're not going to use any formula, it's not a population formula, yeah. A generation is 50. In this case, 1 generation is equal to 52 days. So we have a timeline at T0, we've got 3 females, right? Okay. Right, then what happens? How many are we going to have? What happens to them? After 1 population cycle, after 1 generation, a generation is a population cycle. What's going to be left? So first of all, the original 3 have died, right? So they're gone. Okay. We enter them. So what's it going to be? I've got 3 females. They each had 300 eggs. Of those 300 eggs, how many made it survive? 35%. So there were 900 eggs, of which 35% survived. Yes, because the 3 females each had 300 eggs. This is nothing. This is just a thinking about things question. Okay. I can't use any population formulas for that first part because I don't have a decent population starting point. Okay. Okay, just wait. I'm going to actually use this as my new T0 myself. Okay. So from here to here, okay, after 1 month, after 52 days, in this particular example, how many silkworms does this kid have? 350. So now I'm going to use this as my starting point for Malthusian growth. Because now I've got a mixture of male and females, right? Okay, now, I need to pause for a second. Okay, first of all, okay, so 52 days have passed, right? Okay. They said after 1 year, again, that should really be clearer. 1 year after this, you got the silkworms, right? You got 3 females. So how many days have passed at this point over here? 52 days left, right? Okay. So how many days are left till the end of the year? It's going to be 365 minus 52, right? From here to here, which is 313 days, right? In 313 days, it's quite tough for some. Okay. But are you with me? How many generations, how many population cycles would have passed? Well, how long is the population cycle? 52 days, right? So when we're talking about n in all of these formulas, Pn plus 1 is equal to n is not necessarily years, population cycles, right? So the number of generations or population cycles is going to be 313 divided by 52, right? Which is 6, right? So we have 6 generations have passed in this time interval over there. Okay, so we forget about this part of the sum. This part of the sum is gone. The sum we're working with is this over here. Okay, and the growth is Malthusian. So what I normally do is I write down my formula I'm going to ultimately use. P to the n plus 1 is equal to p to the n. We stick to recursive in this section and let's say it's okay. The only time I wouldn't is if it's like in 500 years' time. Okay. You don't put it out there 500 times. Okay. So in this formula now that we're going to use, what's P0? 350. I'm using this as P0. So what am I looking for? I'm looking for P6, right? What's the problem? The business of R. Okay. If they gave us the birth rate and they gave us the death rate, then R would be equal to birth rate minus death rate. Sometimes they do that, right? Have they done this in this case?
Well, testing.
They've given us some information we can find this. Okay. So first of all, let's look at the death rates. So we're going to use the logic that R is equal to birth rate minus death rate. Okay. Right. Death rate is always easier to find. Now, in one generation, what percentage die? All of them die, right? There's a question today. They die almost immediately after the laying their eggs, right? Okay. So everything's dying, okay, in one generation. If they don't give you the life expectancy, that's normally the case. Okay. So if everything dies, it's 100%. Okay. So death rate is equal to 100%, which is just okay, right now, birth rate. What's the principle for birth rate? Percentage female times number of surviving offspring. Okay, so try to work out the birth rate.
Sir,
Yeah.
if it says like the question says they live on average for 52 days, wouldn't that be?
Oh,
the
did it
life-
say that? Oh, that's what I should have been looking for. No, so they live for 52 days, it says, right? Okay, what's our generation cycle? It's 52 days, right? So they live for 52 days, and your generation cycle is 52 days. In one generation cycle, they will die, right? You'd expect all of them to die, right? That were alive at the beginning of the population cycle. The difference is 1. No, in 52 days.
Oh, wait.
Are those who are alive at the beginning of 52 days? Here we are, right? I'm a silkworm, 52 days, I'm expected to be dead, all of us. Okay, but our children survive. You know, not great for us, but it's not bad for the species. Okay, so death rate is 1, right? Okay, did that answer your question, Zamasa?
Yes, sir.
Okay, I'm assuming it was Zamasa. Right, okay, so the death rate is 1. Okay, Birth rate. Okay, so what did they tell us? The birth rate of how many silkworms does each female have? 300, right? Okay. Of those, okay, what percentage make it? 35%, right? What percentage are females? Use your percent button. 73.5.
Yeah, sorry. No,
Okay. Yeah, so that's 73.5. Massive. Okay. Okay, so your growth rate, so R, which is your intrinsic growth rate, is going to be birth rate minus death rate, which is going to be 73.5 minus the death rate, which is 1. So R is 72.5. Okay, let's talk about percentage now. No, it's not a percentage. Okay, so I end up with, what's my formula going to be? So P to the n plus 1 is equal to P to the n 1 plus R, right? So P to the n plus 1 is equal to P to the n times what? 73.5, eh? There's our formula. Now remember when we said this, if we had this example of a 12% growth rate over here. With a 12% growth rate, okay, the previous question, sorry. With the 12, what was the coefficient? 1.12 was the coefficient, right? So what was the intrinsic growth rate? R was 0.12. Okay, so you minus 1, that gives you the intrinsic growth rate. Okay, and then you times that by 100 to get a percentage. This was a 12% growth rate, right? Okay, so in this case over here, okay, what is your percentage growth rate of these crazy bastards? Okay, next. Sorry. That's 73.5. If I minus 1, I get R, which is 72.5. You've got to times that by 100. The percentage growth rate is 72.5 times by 100. As a percentage. As a percentage, it's 72500. It's going at a rate of 72,500%. So those are going crazy, right? But then each female is popping out. Think of a human population.
Popping out.
If everyone is having 300 babies every 52 days. Okay. Think of the population of the earth, right? Okay. So there's our formula. The question now says, okay, yeah. Have I added one too many more? Sorry. Okay, right. 7,250 still per hour. Right, as a percentage growth. So now, okay, they want to know the population after 1 year, which we said was 6 generations, right? From the beginning. Okay. So we're looking for P0 was equal to P0 315, right? So my calculator, I'm going to go 315 equals. Share your screen. Okay, I would always then write P1. What was P1 equal to? You write it down. What?
20,152.
So that was just after 52 days. That's how many silkworms are on. Okay, right. So then you're going to go 2, 3, 4, 5, 6. Okay. And you're going to have to write down the exponential form. Basically, that crap load of silkworms, right? Okay. So usually, if I'd said it, what it, let's see, what you get your final answer? Okay, it's fine. Either done. 4.97 times 10 to the 13. Yeah, it's fine. I mean, you should read it more. Okay, but it's basically a crap load of silkworms, right? What I normally put is this a realistic model? Does this kid really have 44 billion silkworms? Because it's assuming intrinsic growth, right? First of all, the shoebox that he's got them in, he's not going to be able to make manufacturing silkworms. Okay. Right. Okay. So this is where you start to see the shortcomings of Malthusian models. Now the point, because in reality, what probably happened was this. Okay. In this particular situation, he got up to this many, and the mom said, she went into his room in the middle of the night, took them away, threw away the box. Okay. And he said, sorry, I mean, last night a robber came and started. And he cried for this. But then he was okay because he actually secretly that he had left to go and feed all these monsters. Okay.
Yeah. Like for show and tell. So they brought a box of silkworms and she thought it was so cool that she could like eat one. So she just ate one. And then the teacher like slapped her in front of everyone. So she ate a silkworm in front of all these little kids.
What's that? I'm not too large enough. Okay. Right, time for a break. Okay. Right, people at home, I'm going to leave the meeting and come back on in. Let's aim to start at about 9. We'll have about a 10-minute break. 9:46, round about there. Okay. And I'm going to start. I'm going to start a new. I'm going to set up a new meeting because I want to record the new meeting. Okay.
Okay, sir.
Okay.
Okay, so
Right. Right. Can anyone see a copy? You have to start to get some.
Oh, okay. Yeah. Can I get one? Thank you. No, I need one.
Just wait for me.